So we'll give a couple more minutes for people to trickle in and we'll start. But in the meantime, there's information is right there to go to your browser and type in the tutorial website, the Nabari link, and the coupon for it and all that stuff. So, and we'll have helpers going around, and so if you need any help, definitely just raise your hand at the moment, and later we'll use the sticky notes. Thanks. For those that just arrived, could you raise your hand so we can give you some sticky notes? Anush? Yeah, keep your hand raised for those that doesn't have sticky notes. So yeah, those sticky notes will be, as it says here, pink is for any questions that you may have, or if you're stuck or anything like that. So that helps our helpers go around and help you out. And then aqua is like when there's sections where you get to do stuff. If you're done, just let us know in that way. Yeah. And then logistics-wise, right there is the tutorial website. So this is a rendered version of the tutorial. So if you just want to follow along, sit back, relax, just going along, you could do that. Or if you want to actually play around on the code and everything like that, we use Nabari, and there's the Nabari link. And scipy.quansite.dev. And then there is a special coupon code. So if you've been in previous tutorials that uses Nabari, you might have to re-register for Nabari with the new coupon code. The Nabari team said you can use new email if you need to, it doesn't really matter. as long as you use this coupon code, it's very critical that you use the coupon code so you have access to a larger instance that we will be using. Let me know if the font is too small and I need to. Let me zoom a little more. And then we do have a Slack channel. It's a very long one. So I suggest just go browse and find this tutorial-gen, and then that will pop up. And if you have any questions along the way, throw them in there. Yeah. If you have questions now, let me know. Cool. Well, I'm going to hand over to Vani, and she will introduce all of us.
Good afternoon. Thank you for being here, and thank you to the organizers for organizing this tutorial session, especially setting things up on Nabari. That's making it really easy for us to deliver this tutorial. So I'm Vani Mandava. I'm the head of engineering at the Scientific Software Engineering Center at the eScience Institute at the University of Washington. This tutorial that we are about to deliver is about 6 months of work that from several of us at the center, and I'm going to introduce them quickly. Some of them will be teaching today, and others will be walking around. If you have any questions, if you're blocked on something, put a pink sticky note on your laptop. So Don Setiawan is a research software engineer at the center. Anand is a computer science PhD student at UW, and he's a grad student at the center. Cordero Kaur is also a research software engineer. Anshul, do you want to stand up, Anshul? Is a program manager at the center. Nikki Burgraff is a research software engineer. And Anuj, who's standing over there, is an intern with us and is also a grad student at the University of Washington. Madhav, who's standing in the back, is also a grad student, and he's a student of linguistics, computational linguistics. And finally, Ishika is a research grad student with us, and she is interning this summer at Amazon, but she'll be back with us in the fall. All of us have been involved in some way or other in shaping this tutorial, and we're really excited to bring it to you. A bit of background: the Scientific Software Engineering Center was started a few years ago, about 2.5 years ago, and before the center was started with the goal of helping scientists create reproducible and sustainable and robust software in academia. Most of us have a background in computer science. I had over 2 decades of experience working in tech industry before I took on this role. And I'm very humbled by how extensive the computational science communities and how much they have invested in building really widely adopted open source tools. 6 months after the center started, ChatGPT came out, and all of us know what a tsunami that was. And one of the, even though our goal is to create software for scientists based on what their needs are, we felt the desire, or we felt this gap where there was all this great generative AI innovation that was happening in the computing or the computer science community that wasn't necessarily making its way fast enough to the scientific computing community. There is this saying, my team is probably sick of hearing me say this, but there is this saying that computer scientists solve yesterday's problems with tomorrow's tools, and computational scientists solve tomorrow's problems with yesterday's tools. We were working with scientists who are still working with Fortran and whatnot, and we felt a responsibility to try and apply some of this new generative AI innovation to the problems that scientists were encountering in terms of creating useful software to do good science, to do great science. 2 of the motivations behind how we went about this: one is that there is this misconception with anyone who is entering the space of generative AI that there is a need for GPUs. That is not true. If you're just trying to do inference with generative AI, you can run it on CPUs. Everything that we built here, we built using just our laptops. We have not needed GPUs to build any of this material or to do any of the projects that we have going on right now in the AI space. And then the second one is that in order to use generative AI, you need to have a lot of funding or big budgets. That's not true either. There's a lot of really great models out there. The model that we are using in this is an open source model. The reason we picked this particular model from AI to OLMo is because it has been trained on scientific data. And it's very transparent in how it was trained. The training data and the weights, everything is published. So if anyone wanted to really look under the hood and look at how exactly this model came about and not look at it as such a black box, it is possible to do that. What else? It's always a bit of a balance between how much of the content needs to be sort of foundational and explain some of the basic concepts behind generative AI, how large language models are created, and so on, and making it more of a practitioner type of tutorial where we just teach you how to do stuff, and you can look stuff up in the background. We have tried to strike that balance over here, but if you have any feedback as to specific modules could use more or details in terms of the explanation and so on, please provide that to us. Either you can talk to one of us or provide that in the survey at some point. We used a lot of examples and data from astronomy because the director of eScience Institute happens to be an astronomer, and he gave us a lot of really great data that we could use to play with some of the tooling that we were doing, which is why you see a lot of astronomy-related content here. But the way we have structured this tutorial is you can bring your own data. And the reason for this, a lot of scientists are working with data or content. It could be manuscripts or just a lot of content that is not necessarily published yet. They want to publish it in the future, but there's reams and reams of data that they want to use for their own exploration and for their own AI tooling that they don't necessarily want to give it to ChatGPT because you don't want to back propagate that back to OpenAI or whatever. So the way when you're done with this tutorial today, hopefully if you follow through and get through till the end of it, you will be able to bring your own data to a large language model and build some useful tooling around it. We have done a dry run of this tutorial with a group of scientists at UW about a month ago. So we know that it's very possible. We were able to actually finish that in even a shorter time than what we have allotted today. So with that, enough of this background from me. I will hand it over to the actual instructors, Dawn and Anand, and they can take it away from here. Thank you.
All right. OK, so here's just a quick outline of the what's going to happen today. We have Module 1 to introduce sort of LLM and kind of unveil the black box of an LLM. And then later, Module 2 is more like, let's ask more domain-specific questions and things like that. And then finally, learn about RAG and what that is. And then Module 3 is we're going to demo an application. And then after that, it's just your turn to play around with some textbook that we have. Or if you bring any sort of PDFs or any data that you have, then you could try that too. So we'll just start with the Python environment setup. In this case, we're using Nabari. And again, if you have not been able to log into Nabari, do let us know. And the coupon code is the SciPy large GPU. So let me just go to Nabari here. Oh, and then actually, before I go into Nabari and help you guys set up, here's just kind of what, looking ahead, what we're trying to build here. So some sort of a chat interface, so you can talk to OLMo and ask question. Like in this case, in this example is very trained on astrophysics. So what we've done is we brought in a bunch of like astrophysics abstract from the archive, and then also the AstroPy documentation into a database and things like that, and use that as part of our RAG interface, and you'll understand what RAG is later. But yeah, you can see here, like, these are some of the documents that it pulls. Is really small. Here we go. You can see there some abstracts. And then, the OLMo is able to take those abstracts and create a nice answer from it. And yeah. Oh, yes. How's that? Everybody can read in the back? All right? A little bigger? Okay. So yeah, so here's just a question on what is dark matter. And, it pulls things on like dark matter could be composed of compact dark objects, whatever that is. And whoever is astrophysicist, I'm sure you'll understand some of this. Yeah. Okay, so going back to Nabari, just to make sure everybody, so when you go to scipy.consite.dev, you should have this interface. Let's see. Something like that. And to spawn up an instance, you want to go to Jupyter Lab. So there should be a list of services. Click on Jupyter Lab. And there should be a choices of instances. In my case, it'll just spin up to my actual Jupyter Lab instance because I already chose one. But if you have not, the machine that we'll be using today is, make sure you get the large instance, and there's like multiple large instances, the one with the mist markdown. And then, and then you should have, once that loads up, this view. And I'll give it a few moments just to make sure those that are wanting to follow is able to get this view. We'll come around and help you. And yeah, if you do have this view, please do use your Aqua sticky note. That way then we know we don't need to help you. Need help there. Code, yes. This one. Is everyone able to kind of re-register and stuff like that? Looks like I see a couple that are good to go. Okay, I'm gonna go back now. And if you do already have this, there should be this launcher view, and one of which is the Generative AI Copilot for scientific software. If you click like the download little button here, you should be able to then git clone our repository from GitHub. Yeah, so you have to re-register. So if you log out of Nabari and then go back, there should be a button that says like sign in Keycloak. Click that, there's a register button or something like that. That it says like sign up, do that, and then fill in really anything. You can make a new email if you want. They don't really check, so. and then use the coupon code. And, oh, there we go. Use the same email, different coupon works. We have confirmed.
And if someone has one instance more, then what do you recommend that should be?
It might be very slow on inference. So, yeah. So just, a disclaimer here, we will be using CPU to do inference with the LLM, because our whole point here is not everybody can afford a GPU, and you may just have a bunch of CPUs laying around or a big old server from your past work, so you could just leverage that. So, yeah. Okay. And then once you've downloaded, you should have a folder called tutorials. And then within there, there should be another folder called tutorials, because our repo is called tutorials. And if you have gone to other tutorial like me, you should see other folder, but you want this tutorials. Tutorials. So that is where all of the notebook is going to be in SciPy 2024. And these are all the module notebooks. Question? Okay, so to download tutorials is right here. There should be in the launcher. You have all these choices. This is the one that we want. It's Generative AI Copilot for scientific software. And then click this button here. Yep. Cool. All right. Most people are good. We're ready to start. Looks like most people are good. All right. Then I think that's it for me for now, and I will hand it off to Anant for tutorial number 1.
Thanks, Don. Right, so you enter tutorials, go to SciPy 2024, and you'll see 3 modules over here. Let's go to module 1 and the first notebook over here. We want to be sure that we select the kernel which has the name Gen AI Copilot with RAG. This is the Conda environment which has all the packages we need. So do not use any other environment over here. And the notebooks are fairly self-executable, so please feel free to move on if you think things are slow for you. But in this particular notebook, we will be building a very small statistical text generation language model by ourselves. It won't do a good job. The point of this notebook is to sort of demystify what might be happening underneath these large language models. And these language models have existed forever. I think the oldest paper that I could find was from good enough, 50s. So they've existed since 50s, and there are primarily 2 categories that we could put them in. One is a statistical model, which are techniques like n-grams, HMMs, hidden Markov models, etc., and now the neural networks. And humans are inherently good at learning the probability of these of words, right? So if I ask you, given the prompt or given the text as an input, Jupiter is the largest what? I hope that you can probably through your science training in lower school, you can say that yes, Jupiter is the largest planet, has a higher probability of occurring than Jupiter is the largest moon. And in this notebook, we will be building a small n-gram model. So if we take a sentence such as this, the sun is the solar system's star and by far its most massive component, a unigram or a 1 gram for the above sentence would be this. The sun is the solar system. So it essentially breaks each word into an individual token and gives you a list. A bigram would put 2 words together and then have a moving window and proceed it till your list gets over. So using the same input, if we want to look at the bigram for this sentence, it will be the sun as the first element, sun is as the second element, and so on. And how these models, how the n-gram models work underneath, is that it considers the probability of the given word or the given input, given the n minus 1 previous words. And that's the n in the n-gram. For today's use case, we will be building a trigram model. And what that means is that we will build a text generation model which will generate a word based on the previous 2 words. And if we infinitely keep on doing that, you'll get a sentence or a paragraph. It may not be coherent because you have to work on that separately, but it will still help you generate something. As Don and Vani mentioned, we'll be using an archive dataset. Archive is this place where you can put your published, unpublished research work. Just let's load all the packages we need. SSeek tutorials is sort of a placeholder code that we wrote. It's also public. You can look at it later, but you do not have to really understand what's going underneath. These are helper functions for us to download the data and set up things that we need for this tutorial. This particular function downloads the archive abstracts. And this is the location where you should see the pickled file. And if we read that pickled file and load it into a pandas data frame, this is how it should look. We have 3 columns: ID, title, and abstract. Abstract is just a 300-word explanation of whatever this paper is about. Now, there are about 300K papers in this data set, but for this notebook, we will be just sampling 10,000 just to demonstrate and build this trigram model that we're trying to build over here. This samples 10,000 documents randomly. And if we uncomment this and see, it's still the same data frame. The IDs are all random. Now what we want is we want to start processing our data. So first, we pull out all the rows in the abstract column, stitch them together, and put them under abstracts. And now we are doing something that's preparing your data to create your text generation model. A raw text data could have a ton of things. It could have mathematical symbols. It could have it could be a language that's different than English. And depending on your use case, you have to take care of what is really your data that you want to build your model on. So in this case, we are just removing the extra spaces. We are removing punctuations because we do not care about a full stop or an exclamation as much. And we are also lowercasing all our data because we do not want to distinguish a lowercase letter a or a lowercase word with an uppercase word. An important part of any natural language processing pipeline is tokenizers. think of tokenizers as which could help you break your unstructured data and into discrete elements and so on. In this case, we'll be using Stanford's Natural Language Toolkit, NLTK. We are going to download a tokenizer called Punct, and more on tokenizers later in the upcoming module. So it's fine if you do not understand that word, but think of it in this way: that if I have a paragraph of text, these tools can help me break it into discrete elements and make it consumable for my forthcoming model. So in this case, what I'm doing is I'm feeding the abstracts that I had pulled from my data frame above and sending it to NLTK's tokenized word tokenized function. And if you try to print and see what's in abstract tokens, you'll see this is how it's tokenizing a long text into individual elements. Now, when you encounter any raw text or any blog or article, we have a lot of words like the, a, and, which obviously make the text coherent, but if you're trying to build a distribution model out of these large text, then these are the words that you will encounter a lot. And they'll have like they'll have probabilities which could really be outliers. If you are, let's say, what's the probability of encountering black hole in a sentence? It's probably much less than encountering a or the. And that's one reason that sometimes we remove the stop words. And that's what we're doing over here. If you want to print the stop words, you can see some examples. We are removing the stop words from the array which we had of abstract tokens. And if we again try to print something over here, hopefully this doesn't have all your stop words. That's interesting. I do not know why there are two Z's. Maybe there are different letters, but that I can't infer. So now we try to building a trigram model. What is a trigram? So again, let's see. We're going to call trigrams function of NLTK. And if we send in a list which has all our tokens, this is what it gives out. We have 3 tokens together, and then we again have a moving window, and we keep moving it till we hit the end of the raw text. In this particular cell, all we're doing is we are initializing our model. It doesn't have anything right now. And now, based on our input, which is our abstract tokens, first, we are building a list of trigrams from our abstract tokens over here. And we can see it will give us a list of 3 elements, a list of tuples in which each tuple has 3 tokens. And all we are doing over here is we are computing the frequency of the word given its 2 previous words. Let me know if this piece of code is not clear. All right, now let's see what it did to our model. Over here, we are just randomly sampling whatever exists in our model, given the 2 words black hole. And it gives me this. It's telling me that if I give my model black hole, it's not a probability, but we'll calculate the probability in the next cell. But what it's telling me is that in the raw data, it encountered black hole LMXB once. It encountered black hole irrespective once, and so on. And because we only sampled 10,000 abstracts, everything is 1 in this particular case. And now what we're doing is we are going to transform the frequency into probabilities. And what that does is, if I, again, send my model black hole as an input and sort all the probabilities of the words, it tells me that the mass, the probability of the next word being mass is 0.08. The probability of next word being BH is 0.03. And now you can see that if we have something like this, how we can use this to generate sentences or paragraphs. Yes? No, because up, yes, the question is everyone supposed to see these numbers as I'm getting? The answer is no, because I didn't set the random seed up there when I was sampling the abstracts from our archive data set. Yeah.
Why did you sample such a small number of samples out of the high number of
Right. So the role of this particular notebook is just to demonstrate that we can build something like this. I think given this laptop, this is Don's laptop, and it's very powerful, we could have easily built this model out of 300K abstracts. But engrams can be very computational if you, as you start moving from trigrams to 4 grams, 5 grams, 6 grams. Yeah. Is engrams the same as chunking? Yeah, so engrams is a concept that you can use for building any sort of model. Let's say if you're building a text classification model where you want to do some sentiment analysis, whether this is a positive, negative, or a neutral statement. Engrams is a concept which you can use to build your feature set. How many times in your raw text are these words occurring? That is one feature. Chunking, it really depends on what context you're asking that question. If you're asking that question in the context of how you should prepare your data for a RAG pipeline, let's say, by RAG I mean Retrieval-Augmented Generation, and then my answer will be slightly different. But yeah, they are. I agree with Anshul. They are different things. And this function, all it's doing is given a text as input, it's going to randomly pick a word from the model. So this is the model that we have already trained in the previous cells. Randomly pick a word from there and just append it into a new empty text. And we are just going to generate the first. We are just going to generate 20 words, and we're going to stop that, and we're going to stop then. So if you call this function with the input black hole, this is what it generates. Black hole value, Eddington ratio, Lang sample, and it's very evident that it's not coherent. I had removed all the stop words, so it doesn't really make a lot of sense to me. But underneath, if you wanted to build a text generation model, this is how you would start without training any neural network. And as I mentioned, this was a trigram, but as you can imagine that as you go into 4 grams, 5 grams, this can get computationally very intensive. And in natural language or in any machine learning field, I think cold start is a huge problem for such models. And cold start is, imagine that right now, if in the text that I had sampled, I'm building the model from scratch. But imagine if the black or black hole, these 2 keywords had never occurred in that raw text. And if it wouldn't have occurred, then my model would have thrown some error. We can actually try doing something. Feel free to try in your own notebook and let us know what you find. So clearly, I'm just sending random things over here, and it's throwing me a value error that A cannot be empty unless no samples are taken. And essentially what that means is that in our raw text using which we were building our model, it has never encountered this particular thing. And why will it? Yeah.
You will be considering only literal n-grams, not semantic n-grams? You will be only considering literal n-grams and not semantic n-grams?
Right, so the question is that would we be only including literal n-grams and not semantic n-grams? And yep, as you want to improve these text generation models, you have to start thinking about that.
I meant for this tutorial.
For this tutorial, we won't be using statistical language modeling anymore. Right out of this notebook, we are immediately jumping into the large language model. And underneath over there, yeah, I'm sure while training, they care about semantic and using some contextual embeddings to train there. We don't have to worry about that because we cannot train OLMo in less than an hour. Do people want to share any other concern that people might think this kind of approach could have? Why do we not use these approaches anymore? Like I shared cold start is one big problem.
Isn't overlapping too small if you have only, the overlapping should be larger instead of 3 words per row, which you should have.
Right. It's never clear, do you want to be using trigram, 4gram, I don't know if it's called pentagram or octagram, but it's never really clear, right? Which of these grams should you be using? Yeah. One more time? No memory or context. Right. Once you have trained these models, it's not always clear if you want to, let's say, instead of sending input as 2 words, you want to send in 10 words. It's always going to take in the previous 2 words to generate the model. So you're absolutely right. It has limited context or limited memory as you want to generate more sentences. Yeah. Absolutely, it's very intensive, right? The one big reason of why deep learning and these large language models, or in any application which uses deep learning, is so successful, is because we do not have to do feature engineering as much now. Yeah. Yep, it doesn't know when to stop, and knowing when to stop is a huge concern even in large language models. I don't know how ChatGPT does it, honestly. Like we'll see in the upcoming notebooks that even with OLMo, when do you really stop? How do you tell the model that you're done generating everything? Like you should stop now. It's not always clear, and people have found ways to do it, and we'll see some of that in the upcoming notebooks. But over here, the stopping criteria was that, hey, I just need 20 words, and more often than not, that's what we do. All right. We're going to move to second notebook. And in this notebook, we are done talking about n-grams and statistical language models. We are going to look at LLMs. I think this audience understands this bit that training LLMs is out of our scope, right? And they've been trained over a large amount of textual information, practically the entire internet. We are still learning all the different sources that OpenAI has used for GPT. And early language models, like the one that we just saw could predict the probability of a single word token or n-grams, but these modern language models could practically predict the likelihood of like sentences, paragraphs, entire documents, right? As my friend said, they have large amount memory and context. However, yes, depending on what year the training stopped, you can lead to issues like hallucination. It might generate information that's not factually correct anymore. It maybe would have been correct a few months ago, but not anymore. And similarly, as you get to domain specificity, these LLMs might not really work. As Vani mentioned briefly, we will be using open language model OLMo. It's an open LLM framework built by Allen AI. It's a non-profit research arm which does AI research. It was a spin-off from University of Washington, Seattle. And with this open framework, you can access its complete pre-trained data, training code, model weights, and evaluation suite. And I want to point out that we talk about open source quite a bit, but openness is such a big spectrum. This paper got published recently in FACT 2024. It's one of the conferences which is for fairness, transparency with around machine learning and machine learning applications and methods. And over here, you see this beautiful graph. Over here, you see all these different models. And on the column, you see different parameters on which it's either open or it's not open. So a fun exercise, if we try to find, what's a famous model? If we try to find command R+, it's a very famous model from Cohere AI. We see that it has its reinforcement learning data public. It has its reinforcement learning weights public, which is used, but everything else it's fairly closed. I briefly mentioned this in the notebook one. We'll be using, if you want to look at our internal code that we built, it's also open source and it's available over here, but we do not have to. This particular function just downloads the OLMo model. And this one already exists because it's part of our Nibari setup, I think. So if you go to share and you go to SciPy and this particular folder, SC tutorials, you'll see this particular single file. And let's explore the name of this model slightly. OLMo stands for OLMo. Then we have a couple of keywords that I think it's useful to reflect on what these keywords mean, because if you go to Hugging Face or any paper that mentions their model name, you'll see a pattern that's there. .ggu. So there are 4 things that I want to point out over here. OLMo is straightforward. It's the OLMo model. Then we have 7b, instruct, Q4 underscore K underscore M, and period GGUF. Period GGUF is a GUF format. It's just a format. And it's a format which you can use to do model inference using a tensor library for machine learning called GGML. And there's another abstraction called Llama CPP. It's a C++ framework because C is definitely faster than Python. And what we'll be using a Python binding of Llama CPP to load our OLMo model. So that's what GGUF, I think it's not, GUF or GGUF is all about. Llama CPP is a Python binding of our popular C++ LLM inference framework. Over here, we are just sending the OLMo model path to our model, to this particular argument model path. This particular cell takes a slightly longer because now we are loading the entire model into memory. And there you go. Right, and just with a few lines of code, you have a large language model which has been formatted into GUF, and we also did some post-processing which we'll talk about, but Essentially, it's as easy as this to load a large language model if it's slightly smaller in size. Q4KAM is a technique, or is a descriptor which talks about what kind of quantization we have done. Quantization is a technique, think of it as compression, that's it. These models, when you train, these deep learning models, when you train, if you inspect their model weights, they are floating point values, and they could be 32-bit, they could be really long, and they take up a lot of space when you're storing them. One way of quantization is that you just reduce the 32-bit to 4-bit, and that's what we have done. And there are a plethora of libraries that you can use to convert your model weights and quantize them into different quantization categories. 7B stands for 7 billion. Whenever you look at any model that comes out from any particular institute, they always say whether it's 500 billion, 300 billion, and that's what this particular number stands for. This stands for the number of parameters or hyperparameters that existed in this particular model. Any questions so far related to these 4 keywords that we just looked at? Or anything else that you have seen when you think about the models that you may have seen previously, like what does this particular thing in their name mean?
Earlier you said 7B stands for 7 billion hyperparameters.
Right. Parameters, yeah. Or dimensions, yeah. Or dimensions. Yeah. I'm sorry, I interrupted you. What was your question?
Dimensions. I was trying to understand what kind of parameters.
Oh, so if you imagine you're training a very small, I wish I had a figure over here, but let's say, if you take this particular deep learning network, it's very small. Over here, the number of parameters is 2 plus 3 plus 1, let's say, right? I don't know how they call the number. Maybe they just say that maybe they just calculate this number using the middle layers and not the input and the output layer. That's the input layer, that's the hidden layer in the middle, and that's the output layer. It's possible that they're just calculating that number using the hidden layers, but I think they also use input and output layers to calculate this number. But imagine this, right? So this number is either 3 or 6, but imagine 7 billion. It's impossible to even imagine, I think. But that's what this number means. Yeah.
Yeah, you asked about the model names and this kind of tag, model names. I've seen some models with, they call it abstraction fine-tuning.
Right.
They appear in text.
Yeah, so the question is that sometimes you encounter the word instruction or chat. We will talk about that right after this. Yeah, that's a good question. That's a great question. And in fact, the next piece is about this. So the base models where you do not have that word instruct or chat, these models have been obviously trained on billions of words and text, but their job, I think, is more about text generation, right? So for example, over here, I'm going to ask OLMo, Jupiter is the largest, and that's it. And I'm going to see what it does. And it prints Jupiter is the largest planet, right? And that's the job of a base model. You give it an input text. It tells me what's the probability of the next few words, depending on how much you want it to generate. Over here, I've given the argument max tokens as 1. That's why I'm only asking to generate 1 word. And that's why we get planet over here. But imagine that there was a question. What is the capital of Washington State in the USA? Now, we understand the context and the semantics of this question. We understand that it's asking for the capital name of the Washington State. But imagine if it was a text generation task. How does it really understand that it's a question and I want the answer to the question instead of generating more and more text about this question? And that's where these models which have the keyword instruct or chat come in play. how they are trained is that now you have trained your base models. You use a technique called fine-tuning. So you take a data set. We are going to be using OLMo 7B instruct. And that's the model that we used to quantize and then use it now. And how Alan AI had built this model, OLMo 7B instruct. Is that a question for me? Yeah. Right. Right. I think these particular keywords map to different quantization techniques. I am not that expert of understanding what the nuance between these techniques are, but if you go down this rabbit hole of understanding how quantization works, you will see KV caching, and you'll see all these keywords that basically reflect on what's the method that you have used, I think. Yeah, but definitely verify what I'm saying. Okay. Where was I? Yeah, so I was saying that we are using a model of OLMo 7B. It's called OLMo 7B instruct, which has been further fine-tuned. So probably Alan AI made OLMo 7B base or OLMo 7B, and they further fine-tuned it on a specific data set. There's a link over here, and you can check this out, what this data set does. But it's exactly to take care of these kind of use cases that humans have, right? That we can ask questions, right? We do not, if you want to ask what is the capital of Washington State, I do not want it to generate random text. I want it to answer the question. And that's why you probably want to use instruct or chat models for your use case. Does that kind of answer the question that there was around instruct? Right.
And yes, I can come up with another specific task, not answering the question, but doing something else.
Yeah, that's a right framing. So the response is that it's just like fine tuning, that we have these pre-trained main model, and now we want to fine tune it for whatever task we have. But fine tuning also requires a ton of data. So this data, if I can look at what's the size of this one. It's about 630 megabytes. That's a lot of data. If you think about raw text. Usually for domain-specific applications, it's very hard to build this sort of data set.
Regarding domain-specific applications, can you talk briefly about the temperature parameter?
Yep, that's a great question, and it's great that we have that thing as the next. That means we're doing something right. So these models take, if you inspect the signature of this particular model, you'll see a bunch of parameters that it takes. More or less, all these parameters are consistent between all the different models that exist, and we are only going to look at some. The prompt is the most useful one. It's the input text that the model needs. Max tokens is the number of tokens you want it to generate. Temperature is a value between, I think, 0 to 1. And what people recommend is that if you put the temperature as a lower value, it produces more deterministic output. Basically, it won't be as creative to answer your question. And if you increase the temperature value, it can be a little more creative. Top P is similar like temperature. And the recommendation typically is that you need to either tune temperature or you need to tune top P, but never both together. It's also to control models' output if you want it to be more deterministic or more creative. Stop. We've talked about the stopping criteria briefly. Stop is an argument using which you can tell the model, stop when you encounter this particular word as part of your generation process. And there are different criteria that as well that you can send. Some, if I'm correct, some models also allow you to have a callback based on which you can write more smarter ways to stop generating responses. Frequency penalty is a value again, and what it does is it applies a penalty on the next token generation based on how many times that token has already appeared in the generated response or prompt. And presence penalty is similar, but it provides same penalty for all the repeated tokens. And you can look at other parameters over here if you want to. And over here, I'm going to set the temperature 1 because I want it to be creative. I'm only asking the OLMo to create a nice poem about city of Seattle. I want the max tokens to be 500, and let's see what it generates. Yeah, Llama. So the question is, what is Llama CPP? Llama CPP is a library built in C and C++. It's just for faster model inference. Yes, it's open source. And I think the contributors of Llama CPP and GGML, I think they also have a lot of overlapping contributors for both those packages. Okay, what do we see? Seattle, you're... Okay, I was just making sure that I can read it. Seattle, you're so sick and twisted. Seattle, oh Seattle, a city so strange, with mountains that shout and rain that's more than just show. The coffee is strong, the music is loud, the people are odd. That's weird. But you don't care because this place makes your heart race with its hills and its trees. Yeah, okay. I like it. We were looking at different parameters, and another thing that we have to be mindful of is the context length. Again, whenever you see that some particular organization has open sourced their model or is marketing anything about their large language model, they will say what the context length of that model is. That's a recommended input length that they're asking you to have when you're sending it as an input. It's sort of telling you that if the context length is 2048, do not send me an input prompt which is of 4096 or more than that. You can still do it, but that's what the recommendation is. And now moving on, we'll briefly talk about prompting. And we've been sending these different inputs to our models, right? In the first module, we sent black hole, and now we were sending it text generation task for Jupiter is the largest, what is the city, what is the capital of Washington State in USA? And this is, I think, what mental model I have when I think about prompting. This is my machine. I can make it work using terminal. I can make it work using a browser. I can make it work using all the software tools that are accessible to me. And prompting is a technique which you use to make your large language models usable. Think about it just as an interaction technique, nothing else. And then people are continuously figuring out different ways that they could make these interaction techniques more powerful. And we're going to look at some of them. Typically, in a prompt, we want it to have an instruction set, which is what do I want my model to do? Some context, it's optional, but some context, if your particular instruction set needs it. Depending on the context, some input data. And context and input data are fairly similar in this particular thing that we'll be looking at. And the output indicator, which is how do you want your output to look like? And just like instruct, you'll see sometimes the keyword chat. And a use case for a use case for a chat is where, let's say, you have 10 messages back and forth between your model, and you want to send this entire history of chat to your model for a new question that you might have, right? And that's a chat use case. I was briefly sharing my mental framework, right? What you should think about what prompting is. In each of these models that you look at, the contract of that interaction technique, of how they expect your prompt to look like, can be sometimes shared through a chat template, right? It's a contract. Think of it in this way. The model is telling you that this is how I want the structure of the input to be if you want me to be usable or do something nice for you. And in OLMo, if you do OLMo.metadata, the chat template, this is what the template is. People in our organization have not built this template, right? This template was part of the OLMo model. And in module 2, we will briefly reflect on this a bit more. But for now, just keep this in mind, that prompting is a framework for interacting with the LLM, and these chat templates is that contract, which tells you how you are supposed to format your input to make things work. We're going to talk about just 2 different prompting techniques and move on to the third notebook. The first one is zero-shot prompting. Zero-shot word comes from that you don't know whether the model has ever looked at this particular question before that you want to ask. So I'm going to be using a create chat completion method. This is a function of the Llama CPP Python binding, using which I can send in a list of messages to my model with the specific prompt template that my model expects. So this is what my model expects. It expects a role, user and content. And content is my question or instruction set over here. What I'm asking it to do is I'm giving it a sentence called today's Seattle weather is beautiful. And I'm just asking it to classify whether it's neutral, negative, or positive. The reason that I'm saying this is zero shot is because I don't know whether the model has ever encountered this particular text. We don't know, right? And that's why we're calling it zero shot. It just has never probably encountered this particular text in the training process before. Or we are not giving more context or more information to the model. And let's see what it does. This is a helper function to parse their output. And we see that it says that this particular text is positive, which is correct, because I said today Seattle weather is beautiful. It's probably because of the word beautiful, it's taking the sentiment positive. Right? And note that in this particular prompt, we didn't provide OLMo with any additional context, right? Almost somehow already understands the sentiment, and that's zero shot at work. But what happens if I ask a very relevant question, which is happening today? And I'm asking, did you hear about SciPy 2024 conference? Sorry. And this is zero shot at play. I'm just going to close the other notebook. Okay, let's see what it said. Yeah, this is the cell that I ran. It says, I'm not personally aware of the specific details of the SciPy 2024 conference, as my training data only goes up until September 2021. However, I can provide you with some general information. And that's a good answer, right? It's telling me that the training stopped in September 2021, but it somehow understands that I'm asking a question about 2024, but because the model somehow knows that what SciPy keyword is, because of whatever they encountered in the training process, it can give me relevant information about SciPy conference. And what if I want my response to be a little more, like a little better? And this is what we can do in this particular context. Over here, all I'm doing is using the chat template that the model expects. In the first chat message or interaction, I'm giving it the context, which is what is SciPy 2024 all about. I had copied this particular text from the website a few months ago. And then I'm again asking the question, did you hear about SciPy 2024 conference? And then let's see what it does this time. And do note that the responses can be different. It's because these models are random, and you can control their output using the arguments that we had seen. But whatever I see can be different on your machine.
While this is totally finished,
Yeah.
so large language models like ChatGPT, they don't have current, like today's information, but they still answer if you ask like what was the score to today's game. It comes up with the correct answer.
Mm-hmm.
Is that because they have some augmented search engine on top of the model?
Is that question more relevant for ChatGPT? Or
In general, like if the model does not have today's information,
right? Yeah.
in order to, how do they do that?
Yeah, so this is my understanding. So the question is, how is it that you can ask these models still some relevant information, like ChatGPT, or if you want to give me another example of any model, but you can still ask information about what's happening today or what happened last week. ChatGPT is a beautiful engineering product. It's using GPT-4 or some base model for sure, but it's a great engineering work around that base model, right? Nobody knows what they're doing underneath. People have reflected on.
It can't do that. What you just said. It can't give you historical data. And if I ask who, so Spain played France a couple, 10, 15 minutes ago in the Euro, and I asked who won the Euros match today, and it says, and I think it's designed because, as you just said, training data is only up to January 22. It says for the latest Euro match results, I recommend checking the sports news website, the official UEFA website, or such and such.
You would be surprised. I've done it myself, so I'm not.
I think.
Oh.
So I think this is not a yes or a no question. That we can. It really depends on the question. Yeah.
So there are like other chats that are flexible about this kind of models. So this is a sort of combination of ChatGPT with a search engine. So if you have a question, you can do a Google search, and then you can summarize the Google search via LLMs to you. So it's a combination of a Google search and a pre-trained model. You can do these things at the same time. I think today we might do the RAG approach, which is a similar approach, not in a Google search, in a fixed database, but you can do this on the web, right? You can do a Google search, summarize the results, make it come up with an answer. And these results will be actually this sort that we give here. This combination of an example and
Right. So I cannot exactly paraphrase what you just said, but I know about this API around GPT-4 that you can do a lot of function calling and tool calling, right? So based on specific questions, you can call specific API calls to get the relevant information as well.
Basically,
you wanna say?
via a concept called agents. So these tools like ChatGPT and some of the bigger tools, maybe Gemini as well, these are integrated with a concept called agents, where each agent which is there integrated with the system maybe acts like for a certain job. So an agent could be a calculator, an agent could be a Google search engine, an agent could be just a Wikipedia retrieval thing, kind of like sort of a thing. And once it gets the question, it gets the prompt. The tool is smart enough to analyze like which agent should be approached for getting the answer out from it. And once that is decided, the summary of that answer is like again passed in as a prompt to that system, which gets the answer. So in your case, the agent takes in the question, it decides like, okay, this is a Google search kind of a thing. So if it's integrated with that, you go to Google search, get the answer out of it, pass it through the prompt, pass it as a prompt to the main GPT model which is there, and then summarize the answer.
Are you aware of any open source agents like that?
So it's, I believe like you can design them on your own. Like there are tools, like even if with this system, you can configure it to be extended with a lot of different agents which can club with this concept as well.
So I'm aware of AutoGen. Like it's a multi-agent framework, and in fact, people are going to talk about it. I think tomorrow or day after. But if you just search for agent-based tools on GitHub, I think you will find a plethora of packages which can help you build what you're looking for. Yeah, there's a question over there. Yeah, so the question is, what happens if the new context that you provide, it's conflicting with whatever it has been trained on? We don't know. Yeah, we don't know what happens. This is why it's sometimes so hard to control the large language models, right? A lot of research is happening around safety, around making them more. It's not always clear what might be happening when these kind of conflicting or constraints come out.
I think the true answer to that is that you'll be finished head-to-head in a probabilistic basically match, right? And you'll see which one, regardless of where it comes from, whichever one it thinks is more likely to follow the previous work will win. But I can't answer whether it considers the origin of that.
Right, and that's again, it also becomes an engineering problem then. You have to think about how you want to engineer these things so that you're feeding the relevant context to your prompt in these conflicting situations. We will talk slightly about that in the RAG piece, that given a user query, let's say I fetch 5 or 6 documents from my database, which is relevant as a context to feed into the LLM. What happens if those 5 documents that I've retrieved are conflicting with each other, right? And then it sorts of become more of an engineering problem as to how you want to resolve it, depending on what your downstream application is, I think. All right, so going back to what it generates now. So we stopped at this piece that I had sent some context about SciPy 2024. And then I had asked the question, did you hear about SciPy 2024? And now it is able to give me some correct information, right? It's able to tell me that it's happening at Tahoma Convention Center. It can tell me that the dates are correct, I think. And then it tells me a bit about what this conference does. And just how we were seeing these techniques, RAG is another technique which we are going to use to help the model answer the question that we care about. Do you want? I think now we have a few minutes for people to try their own questions to OLMo. You can use the template. You can use a template from this particular cell. How are we doing on time? Should we proceed with the third notebook, or? Because there's a break in 10 minutes. Okay, so we'll start with the third notebook. Feel free to play around with this particular cell and add your own ask your own questions to OLMo, and then we'll stop at 3 for a 15-minute break. All right, now we'll be looking at LangChain, right? LangChain is, again, open source Python framework, which has a ton of abstractions using which you can build these applications out. And it gives you a structured interface for building and integrating various components of an LLM application, right? It gives you third-party integrations to very quickly move between different models that exist in the world. And also, you do not want to be handcrafting these prompts again and again for your use cases. So it gives you reusable components to basically build out these RAG or any LLM application pipelines to make your code more dry, which is do not repeat yourself. And in this notebook, we'll be going through LangChain and its few components and an important concept called chaining. Prompt templates is a class in LangChain. It is a class which you can use to design these prompts that I was talking about. Imagine that you have a use case where you have an F string as a prompt in which only a few variables change based on your application and doesn't change anything else. Then you can use prompt templates to create your own prompt templates using this particular class. Over here, we're going to load this particular class from LangChain core.prompts. This particular package contains abstractions of different components. And this is a string prompt template, right? So it's a Python F string for all practical use cases. So if I create a prompt template, a planet name, which is my variable in the solar system, is the space, and I send it to from template. Then using this prompt template, I can replace the planet name by calling .format on it. Right? So if I do format now, it will just tell me Mars in the planet solar system it replaces the planet name variable with the planet name, basically. We are again gonna instantiate OLMo. I'm gonna close this old notebook to free up some space. Over here, I am loading the model in OLMo. And now I'm going to send this particular prompt that I had created using the prompt template. I'm going to format it with my planet name Mars and see what response OLMo generates. It says Mars in the solar system is the 4th planet from the sun. That is correct. And this is another way of having two variables as part of a prompt, entity 1, entity 2. Prompt is, I've sent an entity 1 as size, entity 2 as Earth, and I'm asking size of the planet Earth is to OLMo. And this is what it returns. Size of the planet Earth is 4 number meter. The size of the planet Mars is 6 meter, and I don't know why this is happening. Let's see if I do temperature 1, or temperature 0.1. And now it's giving me, is it the right size of planet Earth? Do people know? I don't know. Yeah, it's about roughly correct. But you see that it started saying the diameter of the orbit of, and it stopped because I think the default max tokens is about 20 or 16, but it stopped at an incomplete sentence. And that's coming back to my original argument that stopping criteria is really important when you're doing a text generation task. Yeah? Yeah, so the question is, can you have a grammar-based approach or some natural language processing post hoc thing that you can do on your response? Yes, you absolutely can. I do not know if there is a standard approach of doing it, but reinforcement learning from human feedback partially that's a method that people are using to make sure that their output is correct. But it again requires a lot of data and a lot of human intervention when you're training these models, when you're after the base model is ready. So there are approaches. I do not know if there's a very standard answer to your question though. In your break, definitely try sending in your own F strings and try asking it your own questions. Under LangChain, there is a new concept called a runnable protocol. It allows you to create custom chains, and chains is again which helps you build these different pipelines. That this is my prompt, this is my model, and this is how I want the output to look like, and it helps you build these chains. Over here, now because I want to use this powerful feature, I'm not using the Python binding of Llama CPP from its original package. I'm using Llama CPP from the LangChain community. It's probably the same class with some tweaks, but it allows us to use LangChain features, and that's why I'm using Llama CPP from LangChain this time. And we load the model again. And if you check its type out, you'll see that it's part of LangChain this time. And if we invoke this, .invoke is an important function call. .invoke is your friend when you want to use anything with LangChain. You can call invoke on your prompt templates. You can call invoke on your entire chain of prompt and the model. And it's essentially invoking whatever you want, whatever your input is. So in this case, the input is model. So it's invoking my model with this particular prompt. What is the meaning of life? It tells me why do bad things happen to good people, and so on. This was just a test to make sure that things are running. I've already mentioned this. If you check its type, it's from Llama CPP this time. An important piece over here, which we had talked about previously, is the chat template. I hope you folks remember that. That's the contract, which it talks about what's the format of the input that my model expects. Over here, what I'm doing is I'm accessing the chat template. You can access it using this particular call, olmo.client.metadata. This happens internally. I'm sending it to an argument of template. I'm saying the template format is Jinja2, because the template format can either be a string, an F string, or a Jinja template, and feeding it into a new variable. And this particular prompt template is our prompt template, right, which we can repeatedly invoke now to craft our prompt messages for downstream OLMo applications. I think I'm going to stop here, and let's meet again in 15 minutes. I think this notebook should take about 10 more minutes, and then we'll move to module 2. So before you leave, remember that all we're going to talk about when you come back is these prompt template that we have now, which has been designed from OLMo's chat template, which was decided by OLMo and Alan AI folks that, hey, we want our model to expect the input in this particular format. And we are just setting up, we're just preparing our pipeline to format that input that you want to send to OLMo. Okay. I know Don had a very cool break time over here. Let's meet in 15 minutes. Right, welcome back, folks. We're going to start off where we left. We were discussing the prompt template of OLMo. Over here, we have a new variable of a new object of class prompt template. And if we look at its main attributes, it expects now an input variables. And this is a list of all the input variables that the prompt template expects. And the template is just the actual template that the model uses. So if you look at its input variables, oh no. This shouldn't take this long. Yeah? While we are figuring this out, just a note, we are going to quickly try to finish this notebook, and then there's a longer snack break that's outside?
Yeah.
Okay. Okay, let's just run till the place where loading the OLMo model, we are invoking with this question. Right? And the input variables are going to be add generation prompt, EOS token, and messages. Again, this is not from us, this is from OLMo's template. And if you look at its second attribute of template, you can see the Ginger template that it uses underneath to format all the prompts that we might want to send later on. So we see there are 3 input variables. This is the Ginger template for folks who can read Ginger. It's sort of fairly straightforward. There is an EOS token, which stands for end of sentence token. It is a string that is added at the top of the resulting string after prompt is formatted. And you can see over here where all it's added. Messages is a list of dictionary that is iterated over. Remember the role and the content, that's a list of messages, which each element having 2 keys, role and content. And add generation prompt is a Boolean, right? That's used to tell OLMo that, hey, this is probably a text generation task, or it's a question, or things like that. We had a question earlier about how do we tell the model that it should stop now, or can we have some engineering outside of model that can tell us if the responses that it's generating is incorrect or correct. And add generation prompt, I think, is probably an exercise from the people who have built this model to further give the model a bit more context, whether this is a generation task or it's just a question and answer prompt, and so on. But we have consistently going to be using the Boolean value true and treating everything as a generation task. .invoke can be used to invoke any part of the LangChain pipeline. We have not built the pipeline yet, but that's just an additional context. Over here, we're trying to call invoke, and it's going to fail because wow, it's taking a minute for simpler things now. This shouldn't take this much time. We're not even using OLMo yet. But essentially, you want it to fail. Invoke function expects 2 things. If you look at its signature, it expects an input and a config. And this is how it's supposed to send. Instead of sending just these thing input variables that our model expects directly, we want to send it as part of a dict into the input argument. Let's see if that failed. Wow, okay, it's still running. I think so, yeah. I'm sorry, folks. We'll have to restart the notebook. Is the notebook working fine on everybody else's machine? Or, okay. Maybe I won't call the text generation task this time. We all know the meaning of life this time. I do not want to call this. Okay. Yeah, okay, so it failed, right? And this is what it expects. It expects an input variable, which is our input, again, with the variables that our template expects. And config is an additional config that we'll briefly talk about. It's you can send in different callbacks into the config variable to change how you want your model to generate the output. In this case, we are actually invoking the prompt template to see how the prompt looks afterwards. So we are sending in, this is our instruction set. You are a helpful assistant. Tell me a joke about cats. The role is user. There can be two kinds of roles in for OLMo. One is user, one is assistant. User, typically use it when it's the question or something that's coming from you. Assistant, let OLMo use that particular role. But if, let's say, you want to keep on increasing your context, so let's say you send in a question, OLMo gets back the response, it has the role assistant, and now you want to send in the question and the OLMo response together to answer another question, then keep the role as assistant because you want OLMo to know that this was the response that I had generated, and then a new question is going to come up. Right? So I'm sending all these input variables. This is coming from OLMo. Again, a reminder. And if we do a toString, we can see that this is how it formats the input format. This is not on us. It's all OLMo doing its thing. And this is what gets feeded into OLMo. If you wanted to answer this particular thing, you are a helpful assistant, tell me a joke about cats. This is an end of text that gets appended in the beginning. And this particular token probably is telling OLMo that, hey, you're done seeing the user instruction set. It's your time to start answering the particular question now. Now, we do not want to be doing prompt template.invoke, get the prompt that you want, and then load it into OLMo, and then again call invoke. And that's where chaining helps. In chaining, you can use a pipe operator. It's part of LangChain expression language, LCEL. You can say prompt template, which is your prompt template, and then you pipe it with the model, and then send it to a larger variable, call it LLM chain. And now, instead of doing prompt template invoke or OLMo.invoke, I can directly do LLM chain.invoke because it's a runnable sequence. So if you print a LLM chain, you'll see that the first half is the prompt template. The second half is our model that we had loaded earlier. Right? Again, if you call it invoke, you can see it expects input and config, construct the prompt as expected by OLMo, you are a helpful assistant, and so on. And now you do not have to send, oh, I think this is going to, okay, it already knows that the first dict that you're sending is input, and this is the joke that it prints. Why don't cats play poker in the jungle? Too many lions. I hope that made you smile. Do you need any more amusing animal-themed humor? I can also, okay, the joke was over. Why don't cats play poker in the jungle? Too many lions, I see. And then also ends up explaining a bit more about its own humor. Notice that over here, we are repeatedly sending some parameters that the OLMo expects, which we do not have to, because prompt template also allows you to send another variable as it's called partial variables, where if there are some input variables that OLMo expects, which you know for sure you're going to repeat through your different prompts, you can tell it that, hey, just always make ad generation prompt true. And EOS token, which is the end of sentence token, is always going to be this particular token. Right? I'm going to chain it again because I want it to use this particular prompt template this time. And I'm going to further send a streaming std out callback handler. What this std out callback handler does is that we've been looking at whenever we send OLMo a prompt and ask you to generate something, we have to wait for a few seconds for it to generate something. But in this particular case, because we are sending this particular callback, it's from LangChain again. Hopefully, it generates and outputs the text as we go. And that's happening because of this particular callback. And notice that now, because our prompt template, we had already sent the variables that it needed as partial variables. We do not have to continuously send them in as part of the invoke method. That's it for this notebook. Any questions so far? In the next two notebooks, we'll be going through RAG, and we'll be using your own data. If you have brought some, we're going to try building a RAG chatbot out of it. But any questions so far around this piece? This was just me trying to explain how LangChain works, right? But the takeaway from this notebook is every model has a prompt template which expects that these are the variables that I want, right? I think GPT-4 has 3 kind of roles: user, system, assistant. OLMo only has 2, user and assistant. So the takeaway is just this, that you have to care about how to format your input in a way that your model can do something useful with it. And what we've learned over here is how to do that using LangChain.
Just to clear it up, the instruct model only uses the user and the assistant. But if you use like a base model, like the OLMo base one, 7B, they do have a system role in there where you can basically put in an instruction in that system role. In this case, since the instruct has been trained to like take in a bunch of instructions and stuff, you know, you only need the user role and put all your instructions within the user role. So that's just to clear that up. But yeah, so with a lot of the base models, you see a lot of these system roles.
Yeah. So the question is, what's the difference between pre-training, training, and fine-tuning? Pre-training is, I imagine, anything that you do before your model training starts, right? So it's part of data preparation. It's a data preparation stage. How do you transform your raw data set into something that's usable by the model that you want to train? So that's all under the pre-training phase, I think. And if you start looking at YouTube tutorials around how to even train these models, a lot of arguments exist that 80% of these models are all about data. Everything else, the transformer architecture is great, that's used to train these models, but add or remove a few deep learning layers here and there, it still works great. But data has to be of a very high quality. So that could be probably part of pre-training. Training is when you're actually training your model, right? So you have an input, you have decided that this is the output that you want it to look like, and you propagate your signals and probably improve. You have a loss function which calculates this is how well I'm doing, given this input and an output, and that's a complete different conversation that we can also have. But the typical pipeline would look like that you have your own data, you break it into test and training. In training, you know it's a gold standard data. You know that if this is the input, this is what the output should look like. You create a loss function, which tells you how far away you are from your input and output. Let's say you have an equation, and then if you feed it in this input, it gets an output, and it's way too far away from what the actual output is going to be. The value is probably computed by a loss function, and then you try to optimize on that loss function to reduce it so that your model can really do well on the test data. That's the training phase, right? And that's primarily what when you say you're training a machine learning model, that's primarily what you're doing, right? You're using different optimizers, backpropagation if it's a deep learning method, if it's a deep learning framework, and then you're optimizing on these loss functions. Fine-tuning is that I have these 7 billion parameter model, and I don't know how much time it takes for 7 billion, but if it's, I think the compute age of these large language models goes up into years. It's just practically impossible for us to train it ourselves. That's why Microsoft, Apple, these are the only people who can actually train these large language models because they have that sort of compute. So because you cannot train your own large language model for a lot of reasons, it's expensive. You don't even have that much data. If I'm an astronomer and I have, let's say, even millions of papers, that's nothing in comparison to the internet. So the fine-tuning helps me with this bit. I take a 300 billion parameter, I figure out some compute resources, and then I fine-tune that already pre-trained model. That's a language that they use, a pre-trained model, to fine-tune it on my new data set. And the process is again the same. We have an input, we have some gold standard, we have an input, we know the output, we create a loss function which tells me how well I'm doing, and then I update the model weights, which were those parameters. I update the model weights using backpropagation and other methods, and that's an entirely different field. So this instruct model has been fine-tuned on a specific data set. It's this one. And
And to add on to what Anant was talking about, it also depends on the context in which you're using the terminology. Because if you're talking in terms of fine-tuning as a technique, pre-training, training, and fine-tuning means something a little bit different. So if you're talking, like let's say you're trying to fine-tune for creating a legal chatbot, for instance. The pre-training phase is what we would more or less consider the fine-tuning where you actually aggregate these documents. So 1 million
So we are going to start with the module 2 now. So yeah, at this point, everybody probably have a good grasp on the LM and LLM and prompting and LangChain. And now we're ready to sort of build it all together. I know it has taken quite a bit to get to this point, but I hope you guys, we've sort of unveiled the black box of LLM, and now you have some hands-on practice on it. But yeah, the question remains, how would I utilize this in my own work or organization? Can't I just use ChatGPT? Sure, I mean, you can. However, there's this privacy issue. You may have all these set of documents or GitHub repositories or research papers, unpublished one or something like that, or some domain-specific knowledge bases that you might want to search through quickly. And you might have exploratory questions like, how do I utilize a particular method in a Python package based on your specific context? And what is the current state of research on a particular subtopic? Or you are building an expertise in a new subdomain in your field. So yeah, that sort of thing. Or if you're an organization, maybe you want to create an assistive tool for onboarding new team members, right? And then maybe you have teams of engineers in a sizable, diverse group, and you want to be transparent about what's happening across different projects. And internal documents and things like that is, very sensitive, and you don't want to share to ChatGPT. And, yes, it's fast and it's, convenient, but then again, every time you put something in ChatGPT, it goes to their server, and they have access to that data to keep training their model and fine-tuning it and all these stuff. So yeah, so in this module, we'll be demonstrating how we can use these research abstracts to power question-answer application with OLMo. So as we mentioned before, we use a particular archive data set that is publicly available in Kaggle. So just to show you kind of what we used here. So this is what it is, and it's pretty much all the archive across a lot of STEM papers. But in this particular tutorial, we're using the astrophysics category. So you'll see a lot of astrophysics questions and stuff like that. And then also what we have is we've collected the AstroPy's documentation, so the restructured text from GitHub, and feed it into our vector database. And yeah, and that's going to be the sort of building block, this knowledge base that we will use to help essentially, give answers to the LM, so that the LM is not just, giving you answers from its trained data, but also from the set of documents. All right. So to start with, let's go to the second notebook, the Astrophysics Prompting with OLMo. So as mentioned in the very beginning, we have an in-house astronomer, Professor Andy Connolly, which he gave a lot of these sort of amazing questions that I myself don't know because I am not an astrophysicist. But let's try it out on OLMo and see what OLMo knows. So to start with, again, set up everything, import the Llama CPP class from LangChain community, and then let's set up the OLMo to take in your prompt and stuff like that. So I'd like to highlight these two inputs here to the Llama CPP class, which is the NCTX and the max tokens. So the NCTX is essentially what is the maximum number of tokens for your input. So there's, in this case, is 2048 tokens. And later I will go through what tokens are, but for now, just know that there's this 2048 tokens that it can take at the very max. And if you go beyond that, it will throw an error at you. And as you're exploring later, in later module, when you're playing around with your own documents, you'll see what I mean of this max context. And then there's this max tokens, this is the maximum output tokens that your LLM is going to generate. So in this case, it's 512 tokens. Obviously, if you increase this number, the inference will take longer because it has to, generate more text, things like that. And also, if you increase this input, that also will take longer because now you have a lot more input. So you just have to find the balance between the two to get you the right answer. And then, so we'll set up the prompt template again. Here, I used a partial variable, and in this case, once I've set all that up, all it takes to prompt template is messages. So let's do that. So I'm using this text wrap built-in library and our built-in module, and then so I'm just basically making that pretty, essentially text wrap dedent. But the question that I'm putting in here is, what is dark matter? And then one other thing here in the input content, as part of that, prompt, is this little instruction here. You're an astrophysics expert. Please answer the following question on astrophysics. This will sort of, tell OLMo, like, now put on your astrophysics hat and answer the following question, right? So if we try that, well, right now, the very important thing about prompting is making sure that you are testing out your prompt template to make sure it all works and it looks correct. You can see here what I did, just called the dot format and then put in this input message here with the role user and then the content input content. And you can see here, this is essentially the prompt that will go into OLMo, right? So I think we've seen this is just more of a review. And then I set up the chain again. And this time, I'm going to invoke. So this will take a little bit. But as you can see here, dark matter is a theoretical parameter that counts approximately 84% of the matter in the universe. Anybody here an astrophysicist and can somewhat confirm this answer? No? Huh. Interesting. Okay. Well, there we go. I don't know if that's right or wrong, but it has. So OLMo has been trained in a lot of the archive papers, so it does have something in there for that. But again, as you can see here, it's just generating answers from whatever its trained data is. At this point, I'm not giving any sort of what's called context, so I'm not getting any additional information, just like the example from previous module of asking about the SciPy conference, right? Anand gave the dates and stuff like that as part of the prompt, right? And so I was able to answer that based on that. But in this case, as you can see, nothing about, I didn't say anything, what dark matter is, blah, blah, blah. It's just whatever is the trained data that has been fine-tuned on and stuff. So, okay. So, we've learned about prompting, and there's string prompting, and we've sort of seen this, this variable called partial variables, and now I'm going to introduce you to what's called partial prompts. So partial prompts is used to essentially create a new prompt template from whatever prompt template that you have. I know it's very meta, but yeah, so the input prompt template at the end of the day that I kind of want is this just the instruction and just a simple question, right? However, right now, as you can see here, the built-in, OLMo prompt template for this chat is this confusing Jinja 2 thing, right? And so every time, every time I utilize this prompt template, I have to put in this messages equal blah and things like that, right? And I know for this tutorial, I am creating just a simple chat interface that I can just send in my context, instruction, question to OLMo, and that's it, right? I don't need any other thing. And we're not building anything fancy yet, right? It was just like building a simple question and answer. So nothing like, keep track of, my previous conversation or anything like that. So in order to do that, essentially, I have this input prompt template. I'm putting this in here. So right now you can see here, and if you do prompt template.partial, so there's this function called partial, and then I fill in the messages, and we've seen same thing like you would in formatting a prompt template. You just pass that messages list of dictionary in there. And here I get another prompt template. And this time, you can see here the input variables is nothing. So it's nothing. So there's no more input variables. So now if I do the dot format like we've seen before, I get this new prompt string, which is just this thing, right? So this is the structure that OLMo wants, right? This is the structure that OLMo likes. And so, but in this case, now I have this instruction and this question in a curly braces, right? So now this is just a regular string. So how do we create another, a prompt template using this? And so now we don't have to worry about the confusing Jinja text. Well, you could just do prompt template.from template. I think we've seen this again in previous modules where you were just creating like a very simple, chat completion type of templating. And so yeah, you just do that. And now we have new prompt template. And you can see here, it's expecting input variables as that, right? Instruction and question. And so the instruction is whatever instruction you want, and the question is whatever question that you want. So now you're done. So you have this nice prompt template that then you can pass into the, using LangChain to create a chain and stuff like that. So that's what we're going to do now. So I put this a domain instruction, again, astrophysics instruction. And then in this case, I'm going to ask a different question. How many dimensions are there in elemental abundance of stars? I have no idea. So, but in my case, I put this partial again because I want this instruction. I know that I'm just asking things about astrophysics, but I want different questions, but the same instruction. So I'm just gonna partial variable, like let's partially fill that variable instruction with the domain instruction, and then create the chain again. So this time, as you can see here, when I do invoke, all it is wanting is just this question, a dictionary with a question key. And so now you can just keep doing that, question. And there we go. It thinks it's a mathematician now. So, yeah, so then it's able to then invoke with that question, with that specific domain instruction. So yeah, so with that, I'd like you guys to try out with your own domain a set of questions and see how it responds. So yeah, so you can either copy and paste the code here to use and ask a bunch of the different questions at the very top about astrophysics, or you can change this domain instruction to be, tell it to be like, you're a geologist or oceanographer or something like that, and ask a question about that the answer to, and see how it's going. And yeah, I'll give you guys like 5 minutes or so. And there's this Etherpad. It would be really fun to see, what sort of questions and answers you get from OLMo, because again, OLMo has been trained in a large set of like scientific data, So yeah, see how it does. Any question? Yes.
So I just tried saying, the main instruction, if you're like a historian of Russia, please answer the following question on astrophysics. Ask the same question about astrophysics. And it just gave me like a good answer about the astrophysics question. It kind of ignored the points where I kind of prompted being assumption. Do we know that telling it that it's an expert on such and such actually makes a difference?
So when we play with it, it does make a difference. Though sometimes I'm not quite sure, like exactly under the hood, like how it, if it is, if if it's as accurate as it should be. Like earlier, I asked it to be an astrophysics, and I ask like, something about this dimensionality, and then it's saying I'm not a mathematician, but I didn't say you should be a mathematician. So, but if you don't say like you're an astrophysics and stuff, then it will just give you answer that is not even related sometimes. Let's try it, actually. It does gets you a better output than just the general one, from what we've seen, because it is an instruction that you give it, like be something, like you are an astrophysics, or you are something else, or be more aggressive or something like that. Oh, I see. Anand, do you know if there's a benchmark? The question is like if there's any sort of benchmark sort for like giving that very particular instruction.
deviations or certain phenomena have the same word in each of these 500 fields, right? Now, when it's trying to answer that question, it will refer to the training data where it saw like astrophysics combined with a word, let's say, rocks, meant a different thing, maybe meant out a rock in an outer space, whereas you are a geologist and rock, that meant something else, right? So that's one part of it. And the other part is like when you're providing it at the instruct level, you're making sure that the role remains the same irrespective of how many different kinds of prompts that you're passing into it. The instruction remains the same. Wherein if you're passing it into a prompt, you'll have to specify it again and again. So it's like at base level, one context is set, and then you can provide like different things going into it. And that context can be used in case of like discrepancies, resolve for that discrepancy.
Yeah, thanks for that question. Right. So did anybody put in? All right. You are a clown. I don't physically wear shoes or act like a clown. That's okay. Or dimension. So it still like gives pretty good pretty good answer, I think. It doesn't like being called a clown. But here we go. Metrics for good research software, metrics for evaluating the quality and research software are crucial to measure the effectiveness, usefulness, significance. Oh, that's cool. Look at that. I can say that is a good answer. So yeah, so definitely play around with that, and see how OLMo, works with base OLMo works with your specific domain. Because yeah, now what you've seen is essentially just LLM without any context. So in a bit here, I'm gonna go through finally the RAG, which gives you the context, and that context is this set of documents that you might have. Choose a kernel. Okay. So yeah, so now we'll go to notebook number 3. Before that, I'm gonna shut down all the other ones. Shut down all the kernels. So to do that, just go to the stop with the circle and then click shut down kernels. That way it closes all the notebooks. All right, the moment we've all been waiting for, the Retrieval-Augmented Text Generation RAG framework. So throughout this notebook, we will be exploring RAG, what it is and how it works and why it's so exciting. So why RAG? Although trained on large data sets, stale data can severely limit LLMs. There's these challenges, as I think we've mentioned before, of like if there's new things that come out on the internet, like news articles and stuff like that, it doesn't know that yet, right? Unless you have this sort of very complicated system that has agents that go fetch the web and then come in with the data and all that stuff. And then, yeah, the models that are trained are more generalized, right? They want to cover a whole range of tasks and a whole range of documents and knowledge. So, it doesn't really work if you're in a lab and you have a very specific, set of documents that explain how your lab works. You ask LLM, like, how do I perform, so-and-so, and it doesn't really know, right? Maybe a generalized way of how to perform something it might know, but not a very specific way to your lab. And, I like to give, this mental note of like, maybe, there's one person that is an expert in your lab that knows everything, about the documents in your lab or something, and then that person gets sick or they're overwhelmed with something, and you don't want to keep asking them about that same thing, right? And And so it would be nice to have some sort of assistant that can help fetch those documents for you and synthesize the information. That way, at least you can go in the right direction. So yeah. So here's just a graph of the RAG framework. Oh, let's see. Okay, so essentially, can I make it smaller? There we go. So essentially, RAG is this piece here on the very right, right? So a typical LLM, is just like we've used before. Is user, you have some sort of input query, so some question, and then LLM just generates. So it's this loop over here is the the static type of thing, and then you can like train an LLM for a certain thing, yes, but later we'll go through a kind of pros and cons of fine-tuning versus this RAG base in a second. But then you have this right side, which is there's this indexing that are happening, this embedding that are happening, and there's this sort of retrieval piece that's happening. So essentially, in order for RAG to work, you need some sort of vector store or vector database that can store a lot of these documents that you have. So if you look at this documents into this sort of indexing, essentially, in order to store that document into this index in this database, is what you need to do what's called embedding. And in embedding, essentially, you use another model, a very simplistic model that turns your piece of documents into vectors. And then these vectors go into this vector database. And later we'll see kind of what that vector database does. Or actually, I think in module 1, we sort of see this sort of similarity search that are happening in a small vector. And so that's essentially what's happening. And this vector database is really good at essentially categorizing similar meanings of words basically together. And then when you ask a query, right, and what happens is that query also, this whole text get embedded, using embedding, get turned into, again, vectors, which then be fed in as an input to this vector database. And that's how the query happens, is then the vector database does a complex algorithm to do this sort of similarity search with your documents and stuff like that. And then by the end of that is then you get this okay, after a similarity search, you get some sort of, final vector. Well, and then this final vector is whatever pieces of text in your documents. And that then get, using the embedding model back to words again, and then that's where this relevant document is. So that's essentially what this is, and those pieces of relevant documents then goes back into as part of your prompt here as your context. So now you have essentially instruction, the context, and then the question, which is your query again. And that gets into the LLM. The LLM infers, and then voila, you get your answer. So that's just the overarching what's happening under the hood, but let's dive in a little more detail about each of these pieces. Okay, so RAG, there's 3 main pieces, as I mentioned earlier. There's the retrieval, there's the augmentation, and there's the generation. So here's, retrieval, there's there's 4 or 5 different tasks that are happening during retrieval, which is indexing, query manipulation, data modification, search, and ranking. And in this tutorial, we'll focus on more of the indexing and the search, as that's one thing we're really interested in. So embedding, also called vector embedding, help LLMs develop a semantic understanding of the textual data that they're trained on. So basically, these embedding lay the groundwork for the LLMs to perform tasks like sentence completion, similarity search, question and answer. And okay, let's step back a little bit and sort of what is the differences between fine-tuning and this sort of embedding? Like how do they, when do we do one after one versus the other? As we know, fine-tuning takes a lot of resources, right? You need a lot of GPUs and you need a lot of data, like a lot of data. And I think, we covered a lot on training and embedding with earlier modules. And so with fine-tuning, you wanted to update the parameters of a pre-trained LLM during a task-specific training. So once you fine-tune an LLM, that's it, right? All your data goes into that LLM as part of this trained thing, and it's very fine-tuned on a very specific task. And so when you start asking it another task, it doesn't know how to do that task. And then maybe then that LLM that you fine-tune is not very good for that task or other tasks. So then it's sort of stale and kind of hard to then use. Versus the embedding, so, embedding, you use pre-trained LLM as a feature extractor. So then embedding, you have this, this other mechanism of this vector database that helps you sort of narrow down the information that you need first, right? And so you're not locked into a certain information. You're not locked into a certain task. But then you have this like plethora of information, this knowledge base that you can really leverage, right? And so so that really helps with that. And with this workflow, this RAG of the embedding, it can run in like limited resources, environments. You don't need GPU, and we're demonstrating here with Nabari with only 8 CPU and 32 gig of RAM, right? That's your laptop. We're running in your laptop, this LLM things. Yes, it does take like a minute if you don't do the streaming callback things, but it's free, it's private. You could run this offline if you want. This vector database can run offline as well, things like that. Okay, so I mentioned things about vector, and I think we already kind of seen a little bit about that. Oh, here we go. So we all know about vectors. If you do NumPy array and you just put in multiple numbers as a vector. So that's what it is. And this, where does it go? Okay, this is a vector of size 4. But however, we in the LLM world, we often mention, say things about tokens, right? So what are these tokens? And I mentioned earlier was the maximum tokens, the input tokens, and all this stuff. Well, tokens are just text that are converted into an array of numeric values called vectors. So that's essentially what tokens are. They're just like vectors for the text that you have. And that's sort of the example of the n-grams and stuff like that. You're essentially just tokenizing things. And here, consider this text below, right? Earth is a planet of the solar system. There are 9 planets in the solar system. All planets revolve around the sun. Sun is a star. So you can, case number 1, you could tokenize the entire paragraph into a vector. So when you tokenize the entire paragraph in a single token, you might have sample vector representation maybe like this: 3.1, 6.8, 5.4, 8.0, 7.1. Or if you do, you could tokenize each sentence into vectors. So each of this sort of sentence 1, 2, 3 sentences, you can maybe have this sort of 4 tokens, which is a total of 4 vectors. or you could tokenize each word in a paragraph into a vector. There are 26 words in the paragraph. Ignoring the punctuation, each word gets converted into a vector. So you can see here, totally there's 26 of these such representations. And to tokenize these texts, you need what's called the tokenizers. So tokenizers are components responsible for converting large text into tokens, right? And different types of pre-trained tokenizers are available, and you can train your own tokenizers, but we won't get into that. So yeah, essentially tokenizers break down the original text into tokens, and then these tokens could be characters, subword, word, sentence, paragraph, document levels. It just depends on how these tokenizers have been trained on to split the text. So yeah, so here's just an example of how you can split short sentence to some chunks of text. So this is just a simple thing of like, let's split this text into chunk size of 10, right? So Earth is a planet in the solar system. And so this chunk size is 10 tokens, and then there's this chunk overlap of 0. So if you do that, you do character split. It's actually 4, 1, 2, 3. So yeah, so you split the text. See, yeah, that looks right. Right, because the chunk size max is, hang on a second. Got 4. Right. Okay, anyways, it splits the text. Don't quite remember the details of this character text splitter, but definitely look into the documentation. Yeah, and then so now we have what's called embedding models. So embedding models is a language model that helps essentially embed those texts into basic vectorize them. Again, as I mentioned earlier. So yeah, so embedding models are trained upon these tokens to develop an embedding space. Before training, the embedding model analyzes an n-dimensional vector corresponding to each token with random values. So each embedding model has a maximum like this, the dimension of vectors. And as you can see later, the embedding model that we're using have a certain number of vectors that it essentially, tokenize these whatever text that you have into this embedding space. And an embedding space is an encoded representation of meanings of tokens and inter-token relationships. So embedding space allows this sort of like, if you think of it as like a cloud of words, and then each of in this cloud of words, there may be some groupings depending on the semantic similarity of those words. And so then that allows the sort of vector database to be able to query, your document based on the similarity of this semantic in this embedding space. So yeah, so in this case, we're using this sentence transformers all mini LM L12 V2. So we actually did some evaluation for like various difference of embedding models. And you can check this out in our GitHub here. We actually did some so this is one of the things that you got to do when developing a RAG system is you essentially want to figure out what is the best embedding model for you so that you can get, the best representation of your document. And yeah, so it's pretty fun, we can't log in there. But yeah, so we tried 6 different ones, and for this tutorial, we only looked at the speed of each of the embedding models, not necessarily the the accuracy or anything like that because, because of the limited resources that we have and things like that. But yeah, so here we're just loading in the embedding model. And then using the embedding model. Oh, yes, question. Yes. Well, there are different methods to for it to do those sort of searching, and so that you can calculate what is the most similar things. And the power of the vector database is it knows sort of how to categorize all these different vectors in this embedding space. I think one of my team members is very specialized in vector databases and can speak to this more. So yeah, so there's this word-to-vec technique in NLP for obtaining vector representation of words. And I think this is sort of, one of the underlying algorithm in determining those vector representation of words. But yeah, so here, what I'm gonna do is essentially tell the sentence transformer all-mini LM to embed this word that I have. Earth is a planet in the solar system. Right, so embed query. So this is essentially what happens under the hood when you're passing in the query later for your RAG. Is just it embeds it into a vector. You can see here what our dimension of vector is 384. So you can know sort of what, okay. If you go to the Hugging Face, you can see here kind of the details about this. I think it tells you, where does that tell you the vector or the size? Oh, right here. So this one here, all-mini LM, is a sentence transformers model. So sentence transformer model, if you can look at this, is using this SBERT. And this is a Python modular accessing using training state of our text and image embedding models. Essentially, that model, and it maps sentence and paragraphs to a 384-dimensional dense vector space and can be used for tasks like clustering and semantic search. So in our case, we're doing a semantic search. And yeah, you could see here, you have 384 vector, and there you go. So that is your vectorized representation of this text. Earth is a planet in the solar system. That sort of thing. Yes. The dimensionality of the vectors does not have to be the same. Yeah.
In this case, it doesn't have to be. So yes, when you're comparing multiple documents within user query, then you have to make sure that the embedding model you're using for your user query or prompt is the same as what you use to create the embedding space for your documents. But in this case, we don't care about what the embedding model OLMo is using exactly, because all we want to use embedding is to fetch the relevant documents from disparate elements. And afterwards, it's all text that OLMo is going to do. So once we have the relevant context, once we have a user query, almost internal embeddings takes care of all those things for us. We do not have to make sure that this embedding model is exactly the same as all. It's sort of like isolated from what's happening. Why is it? It seems like you need everybody queries with the vector that's the same as yes, it does. So for no, so for the user query and the vector database, when we are building the vector database, you need to know what embedding model you're using, and we use the same model for that. What I'm saying is that the embedding that OLMo is using underneath, we do not have to. We don't have to exactly match that embedding.
Because what we pass as input to all the model is text, it's not vectors.
Right. And then
Right.
OLMo takes that text and converts it to the embedding space that whatever it needs. But we don't do that.
What if we want to combine the vector space of the model with the vector space of embedded somehow?
What would be the benefit of that?
Because you're limited to the context size. If what you provide to all the model, you're limited to whatever company, what the context limitation is. Well, if you want to provide something bigger than the context, then
That's fine too.
No. So the context length is not dependent on that. The context length is dependent on I send it to user query, I get 5 or 6 relevant documents based on parameters that John will talk about now. I get 5 or 6 documents that are relevant to that user query from my database. And I put them all together, and that's my context length.
It's a two-step process.
Right. So if that goes above, let's say 2048, which was the context length that John had set up for this point, then it might raise an error. The embedding space dimension, it's just an additional thing to know about that when you send in a word, paragraph, sentence, or large number of documents, it's going to shoot out a vector of 384 bits. That's just an additional context that you have to be aware of. That is not, you don't have to, it doesn't have a lot of overlap with the context length. Context length is the LLMs are doing.
Yep. Thanks. All right, so now we're gonna, now we're gonna see how like these different embeddings, compare to each other. So we can, to see how similar two vectors are, you can use, a dot product or use a cosine similarity. So in this case, we're gonna first start with the SciPy spatial distance cosine, and then, as you remember, the query result from the top is Earth is a planet in the solar system. And now we're going to compare that text, that vector representation to this Mars is a planet in the solar system. See how similar they are. And you can see here similarity is 0.79% similar, which is pretty accurate, right? So in this case, when you do a similarity search, these two are most likely to get hit, and like you can actually, get this particular text out of your vector database or something. And then here, if we, compare it to a text call that says "Hello Tacoma," right? We can see here. I don't know why this takes a while. Come on. What's happening? Okay, that should not take a while. Let me restart kernel.
While this is loading, is the vector stored in memory or separate database?
Yeah, so the vector store can be in memory, or it can be in database. Yeah, so that's your index. In our case, we'll be using essentially the vector index is actually on disk. They're like it's just a SQLite under the hood, something like that. Yeah. Okay, here we go. So hello Tacoma, you can see here similarity is 0.09, right? Rounded off. And that's not very similar. So in our case, you know, in a embedding space, these two texts are probably here and like here, right? So, so yeah. So now we go to vector stores, and this is where we save a lot of these vector indexes for each of the documents that we have. Vector store works along the embedding model to create vector embeddings. Vector embeddings are stored in the, in our case, Quadrant vector database collection. So Quadrant is a vector store. It's an open source vector store written in Rust. We all love Python and Rust kind of together. So here we go. And yeah, so what we did was we actually, ahead of time before this tutorial, created this vector database that contains the astrophysics paper and the astrobyte documentation. And if you're interested in how we did all that, Appendix has a lot of resources on this sort of pre-processing that we did to get all this data into the vector database. But later you'll get to sort of hands-on try that out with your own stuff. So yeah, first we're gonna load the Quadrant data path, which is here. So you can see here it's actually within our shared directory, and just to, you know, to show you what that kind of looks like, if you go SciPy, Gen AI, tutorials, SciPy Quadrant, collection, and there's this collection called Archive, Astro, PH Abstract, AstroPy, GitHub, and so on. And you can see here, unveiled under the hood, is just a SQLite database, right, that they use under the hood. So to store all your vector embeddings. Okay, so this is the collection name that we've created. And now with the Quadrant path and the collection name and the embedding model, and I think this gets to the point earlier of like, you know, how you embed your text needs to be the same as your also embedding model and like the output of whatever that vector database is, so that you have the same sort of dimensionality in vector space. But then later on, to get to your LLM and that max token stuff, it gets turned into text. So your LLM is just taking in text in your prompt, and then it does its own magic for embedding under the hood to, you know, convert it into these sort of vector representation under the hood, and then compare that to their own weights that they've been trained on. So yeah, so here we're loading the Quadrant database. And after you load the Quadrant database, we need to have what's called a retriever. Oh no.
Because it's already been opened once through the other stuff, from the other notebook.
Oh, did I?
It's got to be closed.
I didn't open it. Oh. Why isn't this working now? Oh, maybe because we're all accessing the same database. Did not think of that. Okay. Right, because everybody has its own copy. Right, so there's one mistake that I did here. So everyone is trying to access the same exact database. As you know, with accessing the same exact database, it doesn't quite work when you have multiple clients open, unless it's all set up that way. So that's what's happening here. Since we're using this same one here, it doesn't quite work. So what I'm gonna do, I think, see if I can get around that. Do you have any?
Yeah, so basically I faced the same kind of situation. What I did was you change the quadrant folder name, like you get this right. So basically, sorry, I created my own quadrant path. So you extract this, import basically you see your quadrant folder name. I got it from Google Cache, so you can create your own quadrant path right now.
Okay, so sorry guys. Quadrant.
Basically, you have to do this.
Tutorial cache, and then
basically you combine these two to create your new quadrant path.
folder name is that one. Can't I just put in here?
Yeah, so basically then it'll render, create your own vector database collection. You'll have to create a new quadrant collection.
But it might not have the data that we have, so. Well, anyways, I'm just gonna go off of the rendered version at the moment until we can figure this out. Unfortunately, yeah, I did not think about multiple access at the same time. Here we go. So once you have the quadrant client here, what you need to do is create what's called a vector store retriever object. So the vector store retriever allows you to this object allows you to then actually invoke and does these the whole like embedding your query into a vector and then actually then retrieve whatever documents that you have. And so in this case here, instead of just a simple search type similarity, we're using MMR, which stands for maximum marginal relevance. So there is different methods on these sort of what search that you want to do. So MMR selects examples based on a combination of which examples are most similar to the inputs, while also optimizing for diversity. It does this by finding examples with the embeddings that have the greatest cosine similarity with the inputs, and then iteratively adding them with penalizing them for closeness to already selected examples. So we found that MMR was able to get the relevant documents better than just a simple similarity search. And yeah, so, and then this in search quarks, we use K is 2 for essentially I only want the top 2 documents. And so when you invoke what is dark matter, asked that question, what is dark matter, it was able to retrieve the relevant documents for that specific question. And you can see here, here's just a printout of one of the documents. Is one of the greatest scientific enigmas still unsolved. The existence of dark matter is reviewed. Simple gravitational arguments imply most of the mass universe, blah, blah, blah. Right? So this here is actually an abstract of a paper called The Enigma of Dark Matter. And here's sort of the DOI for it, the ID. And yeah, so it's part of, a snippet of that paper. In this case, I think it's the abstract of that paper. Yeah, and oftentimes to make these, this text prettier, we want to sort of format this document object to just a simple, string, so that we can then put, if you remember, put into that prompt template that we have, right? So here in post-processing, there's a little post-processing that we do, which is just a simple function called format docs. And then here, I just basically put new lines for each of the documents, and then do a dot page content to get the actual just page content text. And there we go. So this is what we have. It's just a nice printed string. All right. Okay. So yeah, so we can share the models, but we can't open the database at the same time. Yes, so later on when you try with your own, you'll create your own database collection and your own database, so you won't have any issues with this. Yeah. Okay, so here, we do the same thing. We set up the OLMo model. We set up the prompt template. In our case here, right now we're not doing any of the partial prompting yet, but we will. You'll see later that we will be when we're like putting everything together into some sort of application. But yeah, so we're doing similar thing what we did earlier. Put in the question, but this time there's this context, right? The context is actually using that format docs function. I put in the documents, so the documents object. But those documents object, I want to retrieve that from the retriever. And so then you invoke the question. So then what happens here is that the retriever would just invoke the question, get the relevant documents, format it, and then you have this context string, right? And like earlier what we did, the same instruction, you're an astrophysics expert, please answer the question on astrophysics based on the following context. So here we added an additional instruction called based on the following context. And then the context goes here. So the context is just straight up string text of your document into here. And then after that, the question. In total, at the end of it, you get this, right? This whole thing gets counted in your sort of input token, maximum input token, so that, if you are gonna query like 10 documents or 100 documents and then shove it into the context, it's gonna fail because now you have way too many tokens, right? And the thing I wanna say about this is also, it is really important for you to be able to fetch, the correct documents ahead of time rather than, trying to like query 100 documents for the LLM to sort through and all this stuff. It won't give you the most accurate answer. So it is key to, again, like earlier I mentioned how we sort of explore embedding models and what gives you the most accurate embedding models, and then also play around with this sort of vector database and the different methods of searching through it for the similarity search, that sort of thing is very important in the in sort of the RAG pipeline, right? In the LLM fine tuning, you want a nice training data. Well, here you want a nice like accurate retrieval step, because that's what gives the LLM the the right context for the answer. But yeah, so if you do all that again, and so as you can see here, this time it actually gives you a little more accurate answer than last time when we asked about dark matter. The reason I kind of know that is because like earlier there was no mention about CDOs, compact dark objects, or anything like that, and like or these different masses equation and stuff like that, right? All of this came from the context we give. You can see here there's some sort of mass thing, so it's just really good at like summarizing things and give you that right answer. So if you think of it, my colleague earlier when we had a break, we had a chat of like, think of this as like, you have maybe a PhD person that really knows one thing, right? And they're really smart and really good at things. That's essentially a fine-tuned LLM, right? They're really good, they know one thing, but then now you ask them a different question. Say an oceanographer get asked something with like a health biology question. They won't know, right? I'm like, I don't know anything about the heart or arteries or anything like that, right? However, a PhD oceanographer are good at reading papers, right? So they can just read a paper about some sort of heart thing, and then they can regurgitate the information in a more accurate manner, and you get that more accurate answer. So yeah, so this is essentially what this RAG and context is all about. And yeah, let's see here. And so you can see here again the two difference between without context and with context. And you can see clearly, the two differences where one is pulling in from that text of documents and the other is just from whatever it's been trained on. And yeah, another thing about like if you fine tune on a document, you spend all these hours, but then you might not get the exact text or something like that you want, because it will sort of, you can put the temperature down and be more deterministic, but it's still sort of, it has all these other training materials along with it. But this one, you use mostly the vector. Anyways, question, yes?
So, if we are to like build our own model to do this, leveraging an LLM that's already been trained. So if we download it and we need to populate it with, say, our own documents that we wanted to like generate content from, would we go through this process of doing the layouts, vectorizing, embedding, and stuff of the documents, using the same documents we fed into the LLM to begin with? Or would we be using maybe just a subset of information, or like, it wasn't quite clear if maybe you just use the abstracts just as a way to maybe help accelerate or improve the predictions we would get?
So your question is whether if you already train like a fine-tuned LLM with the documents, right, and then you want to also add on top this sort of RAG-based system. I think in my mind, I feel like the abstracts would be enough to get you there. But
would you be using the same data that you also loaded into the LLM?
what do you guys think? I don't.
So let's imagine a use case, right? Like as you mentioned, you have 1,000 documents lying on your computer or some discrete server, right, which is not publicly ABC company in Q3 of 2022, right? So what's basically happening is that based on this query which you passed into it, the embedding space, which again it consists of all those 1,000 documents, is searched across. It finds the most relevant document out for you, which is, let's say, document number 502 related to the full financial report for 5 years for that company. That context, grabbed with this prompt that you passed in, goes into your LLM model, which is, in this case, is OLMo. So there are two models. Embedding model, whose function is to just retrieve the most similar document based on your prompt that you passed. The answer of that is combined with the actual prompt that you had, and that is being passed on to the LLM model which is there. So you actually did not have to search the space of those 1,000 documents. The embedding model did that for you, and then passed it on to the LLM model. So in short, to answer your question, yes, all those 1,000 documents would be there in the embedding space. It's just that you won't have to then search through it. There already exists a model which searches the most relevant content out for you and passes it on to the LLM model to answer that question. Hopefully, did that answer your question?
So it's still not quite clear. So we download it. In my example, you download that LLM, and so you have your weights and stuff with it, and understand some language. You then give it your 1,000 documents so that it can pull out information from those 1,000 documents. If we do the RAG approach, are we also giving it those, say, 1,000 documents again? So it can then, based on your question, kind of do that search up front to see, hey, this document seems relevant to your query, and then the LLM knows, yeah, you should go to that document.
If you want the specific, if you want the specific document and the specific answer, then I think it's good to have similar ones. So like, for example, right now with OLMo, right, it's been trained on the same data set, right? It's been trained on this archive data set as well under the hood on all the papers and all that stuff. But here we're using the abstracts, right? And it's pulling out the exact abstract that I want based on this relevant question, and it gives me whatever that abstract says, right? And then in this case, then now I could like essentially say like this LLM answer comes from these sources, right? If you didn't do the RAG approach, yes, it's been trained on the same documents, and you ask a question and maybe you get an answer that's sort of relevant to your question. You might get lucky, right? And sometimes if you do like the temperature, say the creative, 1, then it might hallucinate more and just like gives you answers from all over the place based on the weights underneath.
So if you give it the context, it helps
narrow down, yep. So, yeah. Questions? Yeah, so that is in, so we're running out of time, but that is in the try with your data in a bit. So I'm gonna go through the rest of the tutorial.
I think you should skip the application and go straight to
Yes. Yeah, I'll go through really quickly, and then we can go through and play around with that, because we want to make sure that we have time for you guys to really know how to create your own collection. So, all right. So yeah, that's with that context, and like to create this RAG, you need this chain, right? And in our case here, LangChain actually have a convenient function called like create stuff document chain and also create retrieval chain. And as you can see here, again, you set up your prompt template. And here, I just wanted to highlight here, we have this transformed prompt template, which is essentially the, using the partial, now you have this prompt template that only takes context and input. And then you set up this document chain. And then, yeah, with the document chain, you can invoke and like that. But now this time, you can invoke, when you call the invoke, because it's a chain, it will grab the documents and then format that text and then feed it into the LLM. So yeah, so that's that. So I'm gonna go through module 3 since we only have like 25 minutes left. Yeah. So I'm just gonna briefly show this app. So like earlier, I think the very beginning, I showed this, and it's right now it's probably gonna break because the whole database thing. But essentially, this app is made with Panel, and let me just walk you through very quickly here. So Panel allows you to create kind of front end for the app. So this is where you will create front end stuff here. So this interface allows you to put in your text, and then all the things that we've learned so far, all that happens, the prompting and everything happens under the hood. And then what you get is the document showing back, and then the, but to do that, you can see here, you need to create these chains. So here's just a chain that you often would want to create. Is this here context is you give it retriever, which chain up to the show documents, which chain up to format docs and show docs. And format docs are just regular Python function. Definitely check out this notebook and read, the comments and stuff like that. And then this one is runnable pass-through, and this just allows you to get like user input essentially. And yeah. And so all of that, essentially, this is what we're trying to build. Once again, enterprise knowledge base, retrieve the document, embedding model, and then you put in this to a vector database and all that stuff. So okay, cool. That was a very fast walkthrough of that. But I am gonna hand over to Anshul to kind of go through this, try with your data where we get to load our own data set. And I think you have an example. Okay.
I have my example on my computer.
Beautiful. So Anshul have an example of his stuff.
The only thing is,
That's fine.
okay. So, if you could go to module 3 and then get to the second notebook, which is called Try with Your Data. Oh, my bad. There we go. I can pull up the rendered version as well to work through. Mine is a little tainted. So over here, we're going to start by looking into our appendix, in which you'll find in the main directory if you navigate back to SciPy 2024 in appendix. And you're going to want to open 2 of these notebooks. One of them is LangChain document loaders. And that's the way that you can bring in your different types of data. If you have TXT files or Markdown files, if you've got CSVs, if you've got an archive link, which is what we did with the AstroPy abstracts, or if you've got PDFs, which is what I did. And you're also going to need this notebook right here to create your own quadrant database, which answers the question you had earlier, kind of around what's happening under the hood and are we going to have to create our own? And the answer is yes, and I'll show you how forthwith. So you actually don't need to do these imports. I can hide that. But we can begin by going to the quadrant database. Well, actually, never mind. We can begin by doing the retrieve documents right here. And depending on which documents you're working with, or if you'd like to use the data that we direct to right here, you can navigate to the appendix and move over some of the code that is pertinent for whichever document type you want to work with. So if you have anything on your computer that pertains to your field, technical writing, markdown, your own notes, go ahead. Do you have a question? Oh, sorry. Your own notes or anything like that, look at the loader which pertains to that, copy and paste it over here, and also make sure to know where you're placing those documents. So for me, the way we do things at SSeek is we set up a statement of work for all of our projects, and I've dropped those statements of work into the resources folder under data, and then I've specified that, where'd it go? Right here. I put it in the wrong section, that's my bad. But I've specified that right here under PDF folder path. I can give folks a little bit of time to do that. If you don't, like I said, if you don't have your own documents, you can uncomment some of the code here to bring in this algorithms textbook, which we directed to, which works as an example for something to give as context, which will then go into a quadrant database, which we'll set up next. The code for both of these, once again, is under SciPy 2024, appendix, and it's in LangChain document loader, and quadrant vector database creation. Okay. I can navigate to what these files looked like originally to give you a sense of what you should be getting if you're loading in PDFs. These are 3 PDFs of 7 pages each, and it's going to pull them in exactly like that. So you should have 21 total resources. 3 documents of 7 pages each. Once you use the code from this notebook in the appendix, should look like this. You can ask it to tell you what's sitting in each of them, and you're going to rename it all documents. You don't have to do that, but it helps because that's what the quadrant database is going to look for later on. Okay, now we've got them as LangChain document objects, and we can begin with creating our own quadrant databases. We're going to want to grab this code from over here, these imports, and we're also going to want to do these imports, which we set up both here and in the third notebook from the previous module. As we mentioned earlier, these are the embeddings that we're using from Hugging Face. Okay, there we go. Now, this is kind of the tricky part, but you're going to want to, oh man, okay. It's acting up for everybody? Oh, well, all right, let me try refreshing. Let me make sure to save my work. Okay, I'm going to assume that things are preserved. Oh, well, I can check that. Okay, I should be fine. All right, this is where it gets a little bit confusing, but once you've brought in the embeddings model, you're going to want to flip back and forth between the quadrant vector database creation notebook, which is in the appendix, and you're going to want to go back and forth between the quadrant creation subheading and the test out the quadrant collection subheading in the try with your data notebook. And I'm going to begin by verifying the original path. This is where it is. Then I'm going to create a subdirectory within there. You shouldn't call it my turn, because then we'll all run into the same problem that we ran into in the previous one. So I guess I should have picked a better name than my turn. But something that pertains to your use case, you could even just name it after yourself. And that's going to create a subfolder in the quadrant path. Then you can create a name for your collection, which sits in that subfolder. Mine is called University of Washington Scientific Software Engineer Statements of Work. And then you're going to tell it which model to look for. Then this is the biggest chunk of code you're going to have to pull over, which essentially specifies the new collection, ensuring that it's not repeating itself. And it also looks for the documents right here, which we created earlier. All documents. So it takes the LangChain document objects and embeds them in the quadrant collection, which you told it to put underneath this subfolder. Oh, now it's mad at me. Yeah, it's because I just ran mine already. Here I can, yeah. Okay, let me try it again. Okay, there we go. So now it's created a new. So what I did just there was that the error message you just saw earlier was the exact same one that was coming up in the third notebook of the previous module, in that there was already an active connection to the quadrant server, because I had done this myself this morning when I was practicing. So it was trying to open up another one concurrently, which it wasn't happy with. And in order to make sure that it didn't get mad at me again, I followed the instructions from that previous module, where at the end, we make sure to close the client. So that's what I did. I closed my client, which now I can delete this cell, or I can just comment it out. I closed the client. I reran the code which tells it where to put the collection. It opened it up without any issues, and as you can see, it split my 3 PDFs of 7 documents each into 21 documents, each document corresponding to a page. There was a question earlier about chunking. This is essentially chunking. It's basically deciding of the context that you give it in whatever format, how many pieces is it going to break it up into, and you can specify for the model how many pieces is it going to pull out when it looks for context. So you want to make sure that there's big enough that even a small number of pieces has an appropriate number of context, but small enough that it's going to stay within the bounds of your compute or whatever token maxes you've set for the model. This is just asking how many documents are inside. We already know the answer to that. Now we're setting up a retriever, and a retriever is exactly what it sounds like. It's going to go into this SQL database, as Don mentioned, and this is the type of similarity metric that we're interested in. You can use others, and keyword args is basically saying how many of these 21 am I allowed to pull out for context. This is a pretty useful lever to pull, but keep in mind that the higher you go with this, it's going to need a lot more compute. We stuck with 2 when we were doing this on code spaces, and it was breaking on us quite a bit. We moved it down to 1, and it seemed to work, saving us a bit of time. Okay, so here's the first attempt at asking it to pull context based on a question. This is one of our partners, Center for Environmental Forensic Sciences, I think is what it's called. And we're building a Streamlit portal for them. It's a fun project. And I'm asking, what are we doing? We've got, as I mentioned, in these work agreements, you can think of it as an MOU, we've got the software requirements for these projects, and we're asking the model, do you understand that? And can you pull that out for us? So it pulls out from 2 documents, basically a big jumble of text, which it's now considered as context relating to this question, using this similarity metric. There's other ones that might be more refined, better for your use case. It all depends. And you can look at that in any retrieval documentation. Okay, now that we've got the database going, we're going to want to pull in OLMo. This is stuff that we've done before. This is important. These are the levers that we can pull. I know Anant and Don both covered this, but if you want to see what's under the hood in terms of all of your different options, you can make it verbose, and it'll tell you the parameters that are present in the model. And each of these, as Anant covered, has an impact on basically how likely you are to get an answer within your given compute and the nature of the answer itself. For me, because we've got this nice Nabari workspace to play with, I've pumped things up a bit to allow for 1024 context tokens worth of context, and an answer that's 1024 tokens long as well. When we were on code spaces, both of these numbers were, I think, halved. Make sure I ran that. Okay, so this is me asking, Nikki's our engineer who's working on that project, and her name is on the statement of work. So this is me asking OLMo, the pre-trained OLMo, with no fine tuning and no RAG, what is she doing?
and it gave me this nonsensical answer. And it will give me another one about the Indian Navy. So either it's profiling me or it's wrong, or both. And the length of this is not predictable at all. My previous answer, yeah, see? Yeah, it's just hallucinating, yeah. Unbelievable. Oh, this is because I set my max to 1024. Yeah. And then it gives you these basically performance metrics. Now, we're going to do some of the same work to set up the Lang chain using prompt templates. And you can find some of this in, I'm pretty sure, one of these notebooks. Give me 1 second. Yeah, this is already in the original version. We create the prompt template. We've seen. Okay, it's in Module 2 Notebook 3. And it's also in the original Try With Your Data. I didn't have to write this, which is nice. But anyway, here we go. We set up the prompt template. You can set a question for the prompt. I'll do that. We can skip that. You can do that if you'd like, but in the interest of time, I'll move quicker. Okay. And that's on the last page. Okay. All right. Then you're going to want to pull in this from the same notebook that Vani mentioned, because it's what's going to allow you to format your documents once they're retrieved. Let me confirm which notebook that's sitting in. You said Module 2, Notebook 3, Vani? Okay. Yeah, it's right above the augmentation and generation section in Module 2, Notebook 3, the format docs function. We're going to need that to set the context depending on what our question is, which is in the end our goal. Once you do that, you have set up your prompt template. You've got a question. You're telling it how to grab context based on that question. This is similar to what we did earlier, where it's now just pulling out the context, pulling out the documents that are relevant to that context for a given question. We can forget about this. I messed up the order of that, but anyway. Okay, in the interest of time, I'm going to skip this, but this is kind of the reveal. Once you've set up the prompt template, which I showed above, you're going to want to chain it using LangChain. And then you can run it by doing this invoke on your LLM chain, and it should give you an answer. Yeah, it's taking a while. Yeah, I guess because I reloaded it, yeah. Yeah. In the meanwhile, while this is loading, we do have a feedback survey we'd love for you to fill out. It's on the last page at the very bottom, or in the front too. The tiny URL is tinyurl.com/sseekfeedback. SSEC feedback. and it'll take you here. You can also reach out to us. All our emails are on the tutorial for any comments, feedback, any questions, suggestions. Okay, there we go. Based on the context provided, so this is actually interesting. It mixed up two of the labs that we're working with, and it said, based on the context provided, Nikki is working on building a project for the Subramanian lab at UW-Madison. Both of those things are false. For creating an API service framework using these three different analyses to interact with the Streamlit front end. That is true. The project aims to develop a robust, reliable, and well-documented Python code base that can be utilized by researchers in the broader scientific community. That part is true. Additionally, the team intends to establish thorough testing procedures and clear documentation for the code base to ensure its usability and comprehension among researchers beyond the lab. That's also true. So it's not perfect. Maybe if you fed it different data, maybe if you chunked it differently, maybe if you used a different similarity metric when it's searching, if you change the keyword args. If I drop the keyword args to 1 here, it most likely would get it correct because it wouldn't confuse between two documents. If you have context that you're providing that you feel has a lot of similarities, as I mentioned, all 3 documents follow the same formatting, so it's pretty understandable that it could get confused, then maybe you drop the keyword args to 1 and allow it just to focus on one chunk that it's retrieving. I apologize for the speed in this final portion, but it should be pretty straightforward to follow through. And yes, oh, the completed notebook? Yeah, I can do that. I can clean it up and upload it, yeah. Not the data, no. I won't. Yeah, I can upload it, and I can kind of put in placeholders for people to upload their own stuff as well. And then, as I mentioned, the feedback survey you can find here on the last module or at the top. Right there.
And I just want to mention one last thing before everybody leaves is Nabari is not going to be here forever. I think they say it's going to end by the end of the week. So if you want to set up your own locally, we do have this in the Python environment setup, module 1. You can either use GitHub code spaces, or if you have Conda, you could set up your environment Conda for this tutorial and play around with the packages and stuff like that. Yeah, that's it. Thank you all for coming.
Thank you. Awesome. Really good work. Yeah. It also made me understand better what's going on underneath the hood in the quadrant server. That what? Oh my god. Okay. Give me 1 second.
Nobody can access it. You need permission.
Wait, really?
Yes.
God.
Did you not test it in private?
I didn't. Let me see. Oh, Jesus.
Yes.
Okay. Yeah, sorry about that. I'll fix that.
Question about the feedback?
Yeah, there's no permission.
Yeah,
Yes.
let me change that.
Fixing that right now.
Oh, you know what I did? I sent a preview link I sent an edit link rather than a preview.
Yeah, feedback form will be fixing shortly.
Yeah. God. Thank you, Don. My bad. Damn it. Yeah, it's broken. I'm sorry.